Well, he was at that point. He was a teacher, right? Well, he had a teacher's degree, but he wasn't. He didn't have a PhD, so he was thinking about that. But the thing is, at that time, theoretical physics was pretty small, and before that, in the 19th century, physics was all about doing experiments with big stuff and measuring. Around 1900, Lord Kelvin, of the temperature scale, basically said, well, physics is finished. All that rests is stamp collecting. And he meant only just measuring everything better. There's no new things to be found. Well, he was very wrong. But theoretical physics was not a big thing, and there was a lot of theoretical physicists in Germany working at this stuff, and also Einstein, of course. But to find a professor that will help you get your doctorate degree in theoretical physics at that time was very hard. Everybody thinking, yeah, what's the use? What are the applications? I still get that question about all kinds of theoretical science. For instance, all kinds of astronomy. What is the use? That's not the point, of course, but that was the problem at that time. So we had an idea, and he presented it, and basically a couple of months later he retracted it. He wasn't happy with it. Nobody knows what it was about, by the way. So then a year later he writes to a friend that he's basically done with the whole comedy show. He doesn't want to get a doctor's degree. He's bored by it, basically. Okay, so no Dr. Einstein now. Except that, of course, later he did. So he got an idea, and that basically set him to thinking. This was in March 1903, and he started thinking about a way of determining the size of ions and molecules. So from the kinetic gas theory, a couple of decades before, Avogadro's number, you know, they had an idea of the number of molecules in a volume of a gas. Nobody saw a molecule at that time, of course. So he was thinking about determining the size of ions and molecules, but with hydrodynamics in a fluid. So that was the idea for his thesis. This is his thesis, and basically it describes a method to determine the size of molecules in a liquid. And he used, this is basically a liquid of, well, this water with some, I don't know, sugar particles or whatever, dissolved. And these particles have friction, and they diffuse inside the water. And he used, well, a physics model to describe that and find from that the size of particles. And well, they first thought it was too short. It was only 21 pages. Well, some of you have written PhD works, and that they are, well, at least 100 pages usually or more. And 21 pages is very short, but of course, well, fundamental science or theoretical physics can be very dense, so it can be very short. So 21 pages, so okay, but it was of a pretty high level, as you can see. It showed a lot of high and very difficult physics and mathematics. So yeah, it could be, but as I said, theoretical physics was not really appreciated as much as we do now. So it was too short, so what he did was basically add a sentence, and then everything was fine. So okay. So apparently they thought, well, let's just give him the PhD. And that's what he did, but there was still a mistake in the PhD thesis. That mistake was only fixed, or found and fixed, 6 years later, so it wasn't an easy mistake, but you probably can find it, right? You don't see it? Okay. So it's this formula. This is the viscosity. This is the viscosity of a solution without particles dissolved. This is with dissolved. And of course, this phi is the fraction, the volume fraction of the particles that you dissolve. So if that is 0, then of course the viscosities are the same, obviously. But it needs an extra factor of 2.5. Yeah. Why? That's also too hard for me. So there's many things in these articles that I really don't understand. That's way beyond me. I mean, he was Einstein, come on. But there should be a factor 2.5, and it took a student of his, not a student over there, took him 6 years to find the mistake. So okay, it was found, and but basically at that moment Einstein didn't know, and he basically from this formula he found the number, Avogadro's number, and here it is, 2.1 times 10 to the 23rd. So if you know Avogadro's number, that's 6 times that, so that's pretty close. So that's not bad, and that's basically what he said. Oh, it's satisfyingly enough, close enough. So okay, but it was wrong, but only not very wrong. Okay, so at that moment we didn't know how small particles were. So how many there are in one mole? Well, basically it's anybody's guess. But he had this calculation based on liquids. So before they only had calculations of Avogadro's number from gases, right? And the thing is, it's well, we can calculate basically how that works. So if we have 18 grams of water, that takes up 18 milliliters, of course, 18 cubic centimeters of space. And well, we take Avogadro's number but fix it. Okay, so the later value that he found with the correction is pretty close to the actual number. And that means that this volume is divided over, well, that many particles. That means, you don't have to check the numbers, but that means this volume per molecule. And if you, well, spread it out over a sphere, that sphere has a diameter of 0.37 nanometers. Well, it doesn't mean a thing probably, but 37 nanometers, that means this is the space around the molecule. This is not exactly the size of the molecule. The size of the molecule, a water molecule, you probably don't know. I mean, I wouldn't expect you to, but the size of a water molecule is 0.28 nanometers, so pretty close. So there's a pretty good measure for the size of molecules. And the thing is, you need a reality check now. So when was the first molecule photographed? Does anybody know? When did we actually see a molecule? And I don't mean the electron microscope scans of the outside of a molecule where basically you feel the outside electrons, but basically see the structure of a molecule. Does anybody know? There are chemists here. They don't know?
No.
When was this? What do you think? Any idea? This was quite recently, only in 2009. Yeah, 2009. Only then, this is the model, right, of pentacene. They use this molecule. It's a pretty big molecule if you compare it to water, about 5 times as big, roughly. And this was the first molecule that they were able to photograph, and this is how it looks like. But it's pretty good. So the models that they actually teach you guys, they are actually correct, all right? So they didn't know that till 2009, but they worked. But this was the first photo of an actual molecule. So determining the size of a molecule way before that is pretty impressive, actually.